Hello, my name is Solomon and today I'm going to talk about stability. Stability is crucial in biological system because biological cells are usually subject to internal and external disturbance, and understanding how that disturbance affects the normal function of the cell is crucial. And the goal of this presentation is to determine whether the system will diverge from the steady state or return back to the steady state given initial perturbation. And there are two types of stability, the internal and external. And internal stability is the ability of the system to return to a steady state given that one or more steady state variables have been perturbed. As you the system, x naught is going to x, and then the rate function is written as this, and then we get the solution like so. And so as you see, the first part of the solution is called a steady state term, and the second part is a transient term. And we're interested in how the system how the system is returned back to the steady state solution. So we're interested in the second part, which determines the dynamics of the system. Therefore, K2 is negative. So as t increases, the system asymptote reaches to the steady state. So we can conclude that the system is stable. Another way of determining the stability of a system is using the transfer function. And the denominator of the transfer function is called characteristic equation, and setting the numerator to 0, we can get the characteristic polynomial, and from that polynomial we can solve for the poles, and the poles are the eigenvalues, and if the eigenvalues are negative, then the system is stable. And if we have 2D homogeneous system, we can get the Jacobian matrices by taking the derivatives respect to x1 and x2, and by doing the determinant we can get the eigenvalues. And so generally, if all the eigenvalues of the Jacobian matrix have a negative real part, we can conclude that the system is stable. And if the eigenvalues have a complex part, then we can say the system would oscillate, because as you see from Euler formula, the system has cosine and sine which have a periodic function, then the system would oscillate. And another type of stability is external, and this shows if finite change to an element of the system happens, then the system should respond a finite change to internal state change of the system. Then we can say the system is indeed external stable. And to determine whether the system is external stable, we can use the same criteria as internal stability. Another tool that will help us to understand the stability of a system is phase plot. The phase plot refers the space where all possible states can be presented, and so you can understand how the system is diverging away from the steady state or converging towards the steady state solution. And so to demonstrate how the eigenvalues can be used to determine whether the system is stable or not, we can demonstrate on the code. And so as you see, the eigenvalues are both eigenvalues are negative, so we should expect the system should be stable. As you see, all the x1 and x2 are converging towards the steady state value. So, and then you can also see the time plot. So both the x1 and x2 are converging to the steady state solution. So we can conclude that the system is indeed stable. And another plot is, as you see, the eigenvalues are both positive, so we should expect the system diverge away from the state. Indeed, as you see here in the plot, both x1 and x2 are diverging away from the system. Even the the time plot will also show that both x1 and x2 are diverging away from the steady state. And we can also see another plot here. One of the eigenvalues is negative and the other one is positive, And so we should expect the system not to be stable. And here the plot also shows that both x1 and x2 are diverging away from the steady state, and the same happens in the time plot as well. Yeah, and so generally, if the eigenvalues are negative, then we can say the system is stable. And the phase plot is very crucial here because it helps us understand by representing both x1 and x2 and how they respond given a perception to the system. And so the phase plot is very crucial to understand the system. And now let's demonstrate the code. This part is just getting inputs from the user, and this is just typing the title and the differential equation for the user. And this is determining the eigenvalues using the determinant equation. And this is just separating the real and the imaginary part. And this is plotting some. Here is another part which helps to determine the behavior of the system given or by determining the eigenvalues. So depending on the sign and if the eigenvalues contain imaginary part or real part, the system would have a different behavior. So this is all about that. And then this part is just writing out the differential equation in Python, and this is just concatenating of strings because I wasn't able to take the inputs from there to here, so I use a string concatenation. Now I can use this string concatenation to be able to take inputs from the user and to use it right here. And this is just simulating from 0 to 15 in a step of 600. And here is just most of the code. This part is from the book, and so I used the values from there and to plot them here. And so if we test the code, let's see another example. For example, here I give those values. I got those numbers from the book. And I got the eigenvalues here. As you see, they printed out both complex and real, and so, and also you can see the ergon diagram. And so we should expect a spiral node, and here is the result. As you see, the phase plot helps us how x1 and x2 are converging toward the steady state, because both the real part of the eigenmass are positive, and so negative, and so the system should convert. And the time plot also shows here a little oscillating because we saw the eigenvalues have imaginary part, so we should expect to oscillate, and that's what's happening here. And another example is when the eigenvalues are complex and both the real parts are positive, and we should expect the system to be unstable, and that is what's happening. The system is diverging away from the system because both the eigenvalues are, the real part of the eigenvalues are positive. And so also there's oscillating here. That means that there is also imaginary part here. More example, and here this is a pure imaginary part, and so we should expect center node, which is the same. That's what happened, and then oscillation because of the imaginary part. And then more part of my plotting shows that the caption of the plotting shows that the system will show center node corresponding to the complex eigenvalues, and because all the real parts are 0, and then using the matrices 0.5 and B1 and C negative 1 and D negative 0.5, and those values would give us those eigenvalues, and from those eigenvalues we determine the behavior of the system. And thank you.